In this recording, I would like to talk about interest rate sensitivity of bonds. This issue is central to our discussion of Disney's Sleeping Beauty bonds. The sensitivity of the bond price to changes in interest rates depends on primarily three factors. The first factor is the time to maturity or the longevity of the bond. The longer the maturity of the bond is, the more sensitive the bond price to changes in interest rates. The second factor is the coupon interest. The larger the coupon interest is, the lower the bond price sensitivity to changes in interest rates. This is because with larger coupon payments, bond cash flows are more balanced, and as a result, the impact of interest rate changes are distributed over multiple cash flows, and the resulting impact is less severe than the cases where the only cash flow is packed into the principal. If the coupon interest is low, that would be the case where the only cash flow is, or the only large cash flow is going to be towards the end of the maturity of the bond, and that would obviously cause substantial fluctuation in the bond price. Finally, the third term is the yield environment, or the yield itself, or the required rate of return on the bond. In low yield environments, small movements in interest rates move the bond prices substantially. At higher interest rates or higher yield environments, the changes in required rate of return or the bond yield may have more mitigated or modest, let's say, influence on bond prices. So just to summarize what we said is that the longer the term to maturity, the greater is a bond's volatility. The amount of coupon interest, as we mentioned, also impacts bonds price volatility. Specifically, the lower the coupon, the greater will be the bond's volatility, because it will be longer before the investor receives a very significant portion of the cash flow from his or her investment. Most of the cash flows are going to be tacked towards the end of the bond's maturity, and since there's this big chunk of cash flow, any fluctuation in interest rates would have a significant impact on that cash flow, because that is going to be discounted at a pretty high power, and that would drop the price of the bond substantially. In contrast, if the cash flows are balanced out throughout the life of the bond, the impact is going to be less severe. Finally, as we mentioned, yield to maturity is important, or the yield environment is important. At low interest environments, the bond price sensitive to interest rate changes is quite high. And the sensitivity increases with the declining yield to maturity. If the yield to maturity is increasing, the sensitivity declines. This chart very concisely summarizes these three dimensions. As you see in here, the first dimension is the coupon rate, low coupon rate versus high coupon rate. The second dimension is the term to maturity, short term or low maturity and high maturity. And the yield to maturity, or the interest rate environment, low interest rates, high interest rates. As this red quadrant show, the long-term bonds in low yield environments with low coupon rates have the highest volatility. In contrast, the short-term bonds with high coupon interest in high yield environments have the lowest volatility. And we do have these medium volatility cases where there is some mitigating factor. For instance, in this quadrant, although we do have low coupon rates, the term to maturity is low. Again, although the interest rate environment is low, the short-term nature of the bond mitigates the volatility of the bond, and we do have consequently a medium volatility. In this particular case, although the time to maturity is high, the high coupon rate and high yield environment mitigates the volatility, and we do have medium volatility as a result. So these three dimensions are very competently described in this little chart. If you think about the environment that we are in, where we have low interest rates right now, so we are in a low yield environment. Currently, long-term bonds with low coupon rates have very high volatility. So in this environment, the best bond investments in low yield environments, the best bond investments would be the bonds that has high coupon rates and short-term maturities. So that way we could attain a medium volatility because of the environment that we are in. So by increasing the coupon rate and shortening the maturity, we could map ourselves into low to medium volatility environment. So right now, actually, since we are in a low yield environment, low coupon bonds with longer maturities are highly volatile. Actually, it's not a good environment for bond investment at all. So lowest volatility bonds with high coupon rates, short term to maturity in high interest rate environments. Highest volatility bonds are low coupon rates, long term to maturity, and low interest rate environment. So shorter time to maturity, higher coupon rates sort of moderate or mitigate bond volatility. Duration is a measure of bond price volatility. It is actually a measure that combines the length of time to maturity, combines the time to maturity and bond cash flows, and measures the sensitivity of bond value to changes in interest rates. Now, in one definition of duration, we can define duration as some sort of a cash flow weighted average maturity. That also gives us some idea about the sensitivity of the bond price to changes in interest rates. And I'm going to show that connection a little bit, but let's first focus on duration as a measure of cash flow weighted maturity. Obviously, the longer the maturity of the bond is, the more sensitive the bond price to changes in the bond prices, interest rates. So the higher the duration of a bond, higher the sensitivity of the bond value to, or the bond price to interest rate changes. Here is the definition that I made. Duration in this definition is the weighted average of the times until each payment is received, with the weights proportional to the present value of the payment. So what I'm trying to say in here, or what we mean by cash flow weighted average maturity, is that we take the present value of each cash flow that is going to be received at any given time t. We are going to discount that to time 0 and find the weight of that cash flow as compared to the bond value. So this will represent the weight of that particular cash flow that is going to be received at time t. So we are going to do this for each coupon payment, and each time period is going to be weighted with this relative cash flow to the bond price, and the resulting average maturity is going to be the duration of the bond. We call this measure of duration Macaulay duration, because that is crafted by Macaulay, a bond analyst. Duration is shorter than maturity for all bonds except for zero coupon bonds. Zero coupon bonds, since they do have only one cash flow, present value of that cash flow is going to be equal to the bond price. Therefore, this component is going to be 1. And since there's only one cash flow and the multiplier is going to be 1, we are going to get exactly the same figure as the maturity of the bond for duration. So duration is always equal to maturity of the zero coupon bonds. Here is the mechanical process where we calculate the duration of a bond. I will try to describe this. In this particular case, we have a 2-year 8% coupon bond in an environment where the required rate of return on this bond is 10%. So annual interest rate or annualized interest rate or bond equivalent yield on this bond is 10%. This bond is an 8% coupon bond, but it pays interest semi-annually. So we are going to calculate the yield, the duration on this particular bond. So as we described, the method that we use involves each cash flow that the bond pays. Since this is a 8% coupon bond, in the first 6 months or half a year, we're going to receive $40. In the second 6 months or the 1 year point, we're going to receive another $40. In 1.5 years, we are going to receive $40, and in 2 years, we're going to receive principal plus interest, which is $1,040. So now we are going to take each of these cash flows and discount them at the required rate of return 2 times 0. Since this cash flow is going to be received 6 months from now, we are going to divide this into 1 plus 5%, which will give us 38.0.95. The second cash flow is going to be discounted 2 periods by 5% interest rate. So 40 divided by 1 plus 0.05 to the power 2 will give us 36.281. And the third cash flow is going to be discounted at a rate of 1 plus 0.05, but for 3 periods. And in this case, we're going to get 34.554. And finally, the last cash flow is going to be discounted at 1 plus 0.05 to the power 4, which will give us 855,611. When we sum up all of these, obviously we get the bond price. And now we are going to calculate weights as a percentage of the bond price. First cash flow is 3.95% of the bond value. The second one is 3.76% of the bond value. Third one is 3.58% of the bond value. And finally, the last one is the 88.71% of the bond value. And as you see, it all adds up to 1. Now we have the weights and we have the timing of the cash flow. We express the time until payment in terms of years. So 0.5 is going to be multiplied by this weight. So this is T and this is the weight, which is the present value of the cash flow divided by bond value. The multiplication produces 0.0197 and so on. And when we add all of these up, we get the duration of 1.8852. This means that the cash flow weighted maturity of the bond is 1.8852 versus 2 years regular maturity. In the second part, you see a zero coupon bonds duration, which is actually 2. Because we said the zero coupon bonds duration is equal to its time to maturity. So in this case, we calculated an annualized duration by using the Macaulay duration measure. Now, here is another perspective on the bond duration. We can also describe duration as a slope. As you know, the bond price function is a convex function. So duration at any given yield is the slope of the curve at that point. So we could describe duration as the slope of this curve for a given time r, or the yield level r. So the duration is actually delta p over delta dr. So slope of the curve can be described as such, and we could mathematically derive this relationship in the next slide. So if you remember, the bond price formula is something like this. We have cash flows from time t is equal to 1 to time t. The bond price is present value of all of these cash flows, as described in here. So if we take the derivative of this bond price with respect to r, we get this equation in here. So this is the derivative, which is essentially the slope of the continuous slope that we have. That is 1 minus 1 over 1 plus r times t times ct over 1 plus rt. So we're going to do a simple manipulation in here and multiply both sides with 1 over p. And when we do that, the second part of the equation actually contains duration measure that we calculated before. That is the Macaulay duration, which is the weighted average, weighted cash flow weighted average of the maturity. So here, I think it becomes more clear. When we reorganize this formula as such, as you see, time t times the cash flow weights in here, this part is exactly equal to the Macaulay duration, and on the left hand side we have delta p over delta r times 1 over p, and this is equal to minus 1 over 1 plus r, since the slope is negative, since this is a downward sloping convex curve. The slope has a negative sign, and as a result, we can write this equation as delta p over delta r times 1 over p, that is equal to minus 1 over 1 plus r times d. Now, we are going to define a new term that is called modified duration. That is, Macaulay duration divided by 1 plus r is called modified duration. So right in here, we define a new duration measure, which is the d over 1 plus r. And when we substitute that equation in here and move from continuous time to discrete time, we have delta p over p, that is equal to minus delta r times d star, which is the modified duration. And that actually gives us an equation that sort of predicts the change in the bond price for any given change in the interest rate. So given the bond price, modified duration, and a given change in interest rates, we can predict bond price changes. So going into the next slide, we could define the bond price change in duration terms. And as you've seen here, the percentage change in the bond price is proportional to the duration. So for a given percentage change in interest rates, the percentage change in the bond price is proportional to duration. So in this case, actually, we sort of define the duration as some sort of elasticity. That's why I mentioned sensitivity of the bond price changes to interest rates. But eventually, by utilizing modified duration, we can actually derive this nice relationship where we have a prediction of the bond price change for any given interest rate change in here. So when the interest rate changes by delta R for a bond with a modified duration of D and price of P, we expect to have a delta P price change in the bond. So the equation here approximates the change in the bond price for a given change in the yield R and the modified duration. So let's look at a simple example in here just to illustrate this concept that we just introduced. Let's say ABC Incorporated has an outstanding bond with a 10% coupon and 10 years to maturity. And the yield to maturity of the ABC Incorporated bonds is 6%, and the bond has Macaulay duration of 7.16, and the current price of the bond is $1,294.40. Given this, we can calculate the change in the bond price if the required rate of return changes from 6% to 8%. So the question is how much the bond price change when the yield moves from 6% to 8%. So we can answer this question easily because we have all the ingredients that we need. We are trying to figure out this delta P. We have the price of the bond, which is $1,294.40. We know what the Macaulay duration is, which is 7.16. The current yield is 6%, and we are predicting a 2% change in the yield, so delta R is equal to 2%. Now, if we plug in everything into equation, as you know, the modified duration is equal to Macaulay duration divided by 1 plus interest rate, or the yield, which is in this case minus 6.754. And if we plug this into the formula in here, modified duration times change in the yield, which is 2%, times the bond price, which is $1294.40, we get an estimated change of 174.87. So that means that a bond with a modified duration of 6.7 at a current price of $1,294 will experience a $174.87 of price drop when the interest rate increase from 6% to 8%. So as we mentioned, this is just a linear approximation. So it might not be accurate for large changes in interest rates. So if you look at actually in this chart, I calculated the bond price at $12.94, and actual bond price when the interest rate goes up to 8% is going to drop to $1,011.34.20. So that means that the bond price is actually going to decline actually $160.20. But our duration equation predicted a change of $175.10. So our estimate is actually a little bit larger than the actual change. And this is because of the convexity, because the actual bond price relationship with the changes in the yields is convex. But we try to predict that change by using a linear approximation. Therefore, we are a little bit off, and that off is attributable to convexity of the curve that we have. We have a solution for this, but it is beyond the scope of our discussion. That's why I'm not going to talk about that. So there are a few rules that we can review about the duration. as we mentioned earlier, duration of a zero coupon bond equals its time to maturity. The second rule is that holding the maturity constant, a bond's duration is higher when the coupon rate is lower. The third rule is that holding the coupon rate constant, a bond's duration generally increases with its time to maturity. Holding other factors constant, the duration of a coupon bond is higher when the bond's yield to maturity is lower. So as I mentioned you, in lower interest rate environments, the sensitivity of the bond prices to changes in interest rates are significantly higher. Finally, the duration of a level perpetuity is equal to 1 plus R over R. Here is a visual maybe comparison of a 2% coupon and 20% coupon bond. As we said, a higher coupon bond is expected to have lower duration. And you can see that actually this orange line represents the 20% coupon bond. As you can see in here, this curve is flatter than the 2% coupon bond curve. This means that at any given point, the slope on the orange line is smaller than the slopes on blue line. Similarly, we have a 25 and 50-year bonds. Both of them have 2% coupons. The longer maturity bond, which is the 50-year bond in red line, has a much steeper slope at any point as compared to the 25-year bond, which is in the blue line. So this concludes this introduction. We are going to use these thoughts to evaluate sleeping beauty bonds that are issued by Disney in our discussion.